We are, I think, still in chapter 1, and last time we got into the atom and some experiments that led to our understanding of the atom. Again, a reminder that the CRT, which is cathode ray tube, played an important part in our understanding through Thomson, and then followed by Milligan oil drop experiment to really sort of explore electrons. And it was sort of a result of those experiments that came out sort of a early model or theory of the atom, the plum pudding model. And again, that model, as we talked about last time, was thought of as being the sphere positive charge sort of spread out all through the sphere. And within that was embedded electrons, these negatively charged electrons. And again, this sort of positive charged sphere to balance it out. And again, that was sort of the accepted model of the atom where the electrons made up most of the mass of the atom was also a big part of that. And that sort of was pretty good until really the next major sort of development, right, was Rutherford. And Rutherford did his gold foil experiment where he shot alpha particles, which are these positively charged radioactive particles at pieces of gold foil and other metals. Again, as we talked about, because they're moving so fast and they're positively charged, they did expect them to kind of be a little bit deflected as they went through. Remember that what they did find was a little bit surprising. They found that, most of those alpha particles, kind of sailed through with no problem. Every so often, they would bounce off at these large angles, maybe come back at the source. And what they had to do at that point was sort of abandon this model of the atom and come up with really sort of the modern part of the atom here, where the atom is mostly empty space. And again, that is what accounts for those alpha particles just kind of sailing through with no problem. It did have a very dense positive core, which is known as the nucleus, later found to house our protons, which are positively charged. And as we talked about kind of 1930s, neutrons were really sort of discovered, which have no charge there in the nucleus. And the other sort of idea was actually most of the mass of the atom is actually the nucleus. And that makes sense, as we talked about, as we think about our sort of three subatomic particles, our protons, our electrons, and our neutrons. It is the neutrons that is the heaviest, right? Followed very far behind by the electrons, about 1,800 times less massive. It's the least heaviest. And protons and neutrons are fairly close to one another, but the neutrons do just sort of beat out the protons in terms of their mass. So that all does sort of make sense as we think about, again, protons and neutrons are in that nucleus. They're both, again, 1,800 or so times heavier than an electron. So it does make sense most of the mass of the atom is that nucleus. Because the nucleus is ultimately positively charged, within that empty space, we have our electrons, again, flying around randomly. There is, as we talked about as well last time, an attraction between the electrons, which are negatively charged, and the nucleus, which is ultimately positively charged. As we talked about, that's sort of what kind of keeps them there, kind of ties them to the atom, so they just don't kind of fly away. And as we'll talk about in later chapters as well, again, that's what really accounts for why certain electrons may be involved in bonding and other ones are not involved in bonding based on their position to the nucleus. Any questions on any of that there that we talked about? All right. So I think we're somewhere in this ballpark. So the chemistry of atoms does come from electrons, and they're involved when atoms come together. So if you just think about sort of the structure of atoms, electrons are on the outside flying around. So it does make sense that when two atoms come together, they are really the first ones to say hello to each other as they're on the outside. All chemical reactions, as you may know or may not know, again, only involve really electrons. So when we have a chemical reaction, again, the only thing that's happening is we're breaking bonds and making bonds. So electrons really are the only thing involved. Nothing in the nucleus is involved in a chemical reaction. That's also why, as we'll talk about, we have conservation of elements. For example, we don't like lose a carbon along the way, or make a carbon along the way. Whatever number of carbons we start with is the same number of carbons we end with, because really nothing in the nucleus changes. So that's why we really don't kind of make new elements in a chemical reaction, or really lose elements in a chemical reaction, because it's all about really breaking the bonds that hold all those elements and atoms together, or atoms of those elements together, and just rearranging them and kind of putting them back together in different sort of compounds. So some of the important properties of an atom we're going to talk about now: atomic number, mass number, and isotopes. And the first thing we're going to talk about are isotopes. And isotopes, come back, there you go. Isotopes are atoms have the same number of protons, but a different number of neutrons. The chemistry of isotopes are pretty much identical. They pretty much will do the same thing, again, because electrons are what's bonding there, but they will do basically the same thing. Some isotopes are radioactive, some are not. And isotopes basically have a different number of neutrons. And this is one of those things, for example, Dalton's atomic theory that we talked about, that was found later on to be not so correct. Again, he originally said, or he did say, that atoms of the same element are identical to each other. And again, the existence of these isotopes sort of disproved Dalton's atomic theory, or part of it, as obviously they have different neutrons and different masses. So these are two isotopes of sodium. They both have 11 protons. One has 12 neutrons. The other one has 13 neutrons. And again, that is the difference between them, is those two things. So let's talk a little about atomic number. Atomic number is the number of protons there are in an atom. And the atomic number is sometimes abbreviated with a Z. If you go to the periodic table and you look on the periodic table, you see the number that is above the symbol. That is the atomic number. So you can't find the atomic number on the periodic table. It's the one that's typically above the symbol. On the one on the wall up to the right of the symbol is the atomic number. The definition of the atomic number is the number of protons there are in an atom. But if you do have a neutral atom, that would also tell you the number of electrons, since the only three particles in an atom are protons, electrons, and neutrons. So if we know how many protons there are that are positive, neutrons don't really matter because they're neutral. That would also tell us the number of electrons. It's also really important to understand that the definition, as I just mentioned, is actually just the number of protons. So if you're asked a question or see a question that says, what is the definition of atomic number? The actual definition is just protons. It has nothing to do with electrons. The side note to that is, again, in a neutral situation, it will tell you the number of electrons you have. So if we look at our friend nitrogen there on the periodic table, got like a lucky number 7 there. That means in a neutral nitrogen atom, you would have 7 protons, which are positive. You would also have a matching amount of electrons, which are negative. And that gives you an overall charge of 0 for that particular atom, as all the positives and negatives basically cancel each other out. So atomic number of protons, sometimes again abbreviated with the letter Z to represent the atomic number. The next type of number that's important is the mass number. And the mass number is sometimes abbreviated with an A. The definition of the mass number is the number of protons and the number of neutrons there are in an atom. And that's quite important, because if you take the mass number, which is essentially your number of protons plus your number of neutrons, and you take the atomic number that we just talked about there on the last slide, which is the number of protons, and you subtract those two, that will give you the number of neutrons there are in an atom. So if you take the mass number minus the atomic number, that will give you the number of neutrons that are present. Every element will have protons, electrons, and neutrons. The exception is hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron. Hydrogen has some interesting properties, which is, why perhaps it's on the left-hand side of the periodic table there. Old periodic tables, they used to put it on both sides, left and right of the periodic table. But hydrogen doesn't have any neutrons, just a proton and an electron. All other elements will have protons, electrons, and neutrons. When you calculate any of those things, the number of protons, electrons, neutrons, atomic number, mass number, they all should be positive whole numbers. So they always should be whole numbers, positive whole numbers, all those things. That is why when we look at the periodic table there, can we find our friend the mass number on the periodic table? The answer is no, you cannot. This right here is not the mass number, because the definition we just talked about was they all need to be whole numbers. If you look at pretty much all those numbers on the bottom of the periodic table, pretty much not, most of them are not whole numbers. They're mostly decimal numbers. This is something we'll talk about later on. This is the atomic mass and also the molar mass, but it is not the mass number. So you cannot find the mass number on the periodic table. You can only find the atomic number on the periodic table. Yes, sir. It's used to it's used for a couple of things, but it's used to figure out obviously how many neutrons something has. It's also used obviously just as an identifier as to what isotope of the element you may be talking about. And for that straight up calculations, not too much in terms of using it for a calculation other than maybe figuring out how many neutrons and stuff like that. You could also use it, as we'll talk about, for atomic mass. That's where all those numbers on the bottom come from. All the naturally occurring isotopes of a particular element is where you get that number from. So the atomic mass is that number on the bottom, not the mass number. You will also notice, and maybe we should go back here and take a look here at the atomic number. I guess we'll do that here. The atomic number, which is the top number, right? If we look at the periodic table at that top number, which is the atomic number, none of them repeat, right? So just like the bottom number, they're all pretty much decimals. None of the atomic numbers repeat on the periodic table. Every element has its own unique atomic number, which is really important because that should tell you that out of protons, electrons, and neutrons, which one is the most important to know in terms of what element it's going to be. It is protons, which is the atomic number. So if you know the number of protons, which means you do know the atomic number, and you have a periodic table, you should know what element you're dealing with. For example, you will never have a carbon atom that has an atomic number of like 4, because the atomic number 4 up there is beryllium, right? So that's actually who has 4 protons. So out of all those, the protons are the most important. That is also why, as I was talking about earlier, when we have a chemical reaction where the only thing that gets touched are electrons, we don't touch any of the protons. That's why we have the conservation of those elements. That's why we don't change elements, because we don't do anything with the protons. They remain the same from beginning to end, and that element then remains obviously the same from beginning to end. The only time that really does change is in nuclear reactions, because all you do is change protons, neutrons, and really protons. And that's why we don't have conservation of elements when you have like a nuclear reaction. But in a chemical reaction like we talk about here, everything is conserved. So that's again why we start with 6 carbons. We should end with 6 carbons. Now, in most cases, as I mentioned, we do have isotopes. So for example, hydrogen has 1 proton, no neutron. Deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. And tritium has 1 proton and 2 neutrons. Tritium is basically the radioactive version of hydrogen. And we sometimes write isotopes like we see here on the bottom. We use the symbol, and on the top left, we put the mass number. And on the bottom left there, we go atomic number. So for example, if we were going to write sort of the symbols here for each of these, If I wasn't sure what the symbol was for hydrogen, basically I'd go to periodic table because it has one proton and find number 1, and it should tell me H for hydrogen. 1 proton is also the atomic number, which means it should go on the bottom. Here, protons plus neutrons is our mass number, so that's 1 plus 0, which would give us 1. So that would be the symbol for hydrogen, with both the mass number on top and the atomic number on the bottom. Again, to find the number of neutrons, top number minus bottom number gives you the number of neutrons, so 1 minus 1 is 0 in this case. Now I come over here, and this doesn't even sound like hydrogen, but what I do know, it has 1 proton, so when I go to the periodic table, even though it doesn't sound like hydrogen, it is hydrogen because it has 1 proton. Also still has 1 for its atomic number as well. And 1 proton plus 1 neutron gives us a 2 for our mass number. And once again, if we take the top number minus the bottom number, 2 minus 1 is 1. And that would give us our number of neutrons. And tritium, again, doesn't sound like hydrogen, but it has 1 proton, which will give you the hydrogen symbol. And in this case, obviously 1 plus 2 is 3, and that would be our mass number. So again, this is very common how isotopes are written: mass number top left, atomic number bottom left there. Another way that sometimes you will see a isotope written is something like this, say Cu64. That is copper 64. If you had to take a guess, the 64 is which number? Mass number, atomic number? It is the mass number, and the reason, again, I do know it's the mass number because if I go to the periodic table, I can clearly see that copper is 29 up there, and that would be its atomic number. So if we kind of did the other way of writing it, copper 29 would go on the bottom, 64 would go here on the top left for the mass number. And that would mean in this case, the number of protons is going to be 29. We would have an equal number of electrons in this case. Again, all those positives and all those negatives basically cancel each other out. We do know that it doesn't have a charge because, frankly, if it did have a charge, we would see something written here. So we don't see anything written there. We could assume that it is neutral. Number of neutrons in this case would be 64 minus 29, like 35, I think. And that is what we would have in that situation. Any questions on that there? All right, so why don't you maybe try some, I think? Yeah. So for each of these, why don't you do number of protons, electrons, and neutrons for each of these guys here? Okay, so let's take a look, see how you're doing. So once again here, top number going to be our mass number, which is our protons and our neutrons. Bottom number there going to be our atomic number we could get from the periodic table, which is our protons. So in this particular case, CO, which is cobalt, in terms of protons, should have 27 positive protons. Because it has no charge, again, nothing is written there. Again, should have an equal number of electrons. It gives you basically no charge overall. Number of neutrons in this case, top number, mass number minus atomic number, 33. Any questions on that one there? Cl, which is chlorine, once again, no charge happening there. So proton's going to be the atomic number on the bottom, 17. Because it's neutral, it will then have a matching number of electrons to give us no charge. And in this case, our number of neutrons would be 37 minus 17. Looks like a 20 in that particular case. And lastly here, U, which is uranium. Once again, no charge written. Atomic number there on the bottom. So our protons would be 92. Once again, needs a matching number of electrons to give it no charge. And our number of neutrons equals 238 minus 92. That's a lot. Buck 46 maybe, yeah, in terms of neutrons. Any questions on any of those there? All right, let's take a look at a couple more here maybe. All right, so for each of these, why don't you write the formula with the mass number and atomic number, or the symbol with the mass number and the atomic number. If you don't have a periodic table, you can see that is what krypton looks like up there. Obviously, nitrogen looks like that, and iron looks like 25, I think, or 26, like 25. But so on this one, krypton, which is Kr, so clear if it wasn't provided to you, you should go to periodic table. That periodic table is going to give you the atomic number there, and that's going to be 36. That 36 is also the number of protons. Here they give us that it has 48 neutrons. And if you add those together, that gets you 84, which is the mass number in this case, which would be 84. Any questions on that one? Next is nitrogen. Once again, going to periodic table, we see 7 for the atomic number. So that's going to go there on the bottom. That again also means it has 7 protons plus 6 neutrons, which again, if we add that together, will give us our mass number of 13, which will look something like so. And lastly here, we're looking for iron, which is Fe. From the periodic table there, if you wrote the right number the first time, we would have 26 there. In this particular case, they actually gave us the mass number, which was 56. That means here, iron, in terms of protons, has 26. It also would have, in terms of electrons, a matching 26, give you no charge. And in terms of neutrons, in this case, mass number 56 minus atomic 26 would give you a 30 in this case. Yeah. Any questions on mass number, atomic number, protons, electrons, neutrons? Now, what would happen if we did have something, for example, that did have a charge, right? So if we had something that did have a charge, things with charges are known as ions, and there's 2 types of charged things. There are cations, which are positively charged, and again, there are anions, which are negatively charged. So for example, if we take our nitrogen there, and we have this same guy, but it has a -3 charge in this case. What's going to be affected? Well, we know in this case, in terms of the number of neutrons, it is the same as 13 minus 7, which is 6. We also know that that is the atomic number, which means the number of protons is going to be 7 in this case. So that does leave us only electrons here that will change. So when something does gain a charge, either a positive charge or a negative charge, it is only the electrons that actually change. We know as well it cannot be the protons, because if we do that, then it's no longer the same element. So the element would change. So that never changes. And obviously neutrons have no charge, so they're not going to affect anything. So in this particular case, the number of electrons would actually be 10 in this case. 10 negative things plus 7 positive things leaves you a -3 left over, which is where that charge comes from. It has 3 more electrons than it started with over here. Over here it had 7 protons and 7 electrons in its neutral state. And that's what an anion is, negatively charged. The negative tells you that it has gained electrons, and the actual number tells you how many it gained from the neutral sort of atom of it. Now, if we look at iron, which has, we'll go with a +2 in this situation. Why not? We'll do the same numbers here. So once again, since our mass number and atomic number are the same, our number of neutrons are also going to be the same here. We're going to end up with 30. Once again, it is still iron, which means it still has an atomic number of 26. So the number of protons here is going to be 26 positive guys. That means how many electrons would I have in this case? 24. Yeah. 26 positive things plus 24 negative things leaves you a plus 2 left over, which once again is where the charge comes from. So what happened if you look at iron versus its neutral and the one with the plus 2 charge, it lost 2 electrons from its neutral state, and that's what the positive means. It loses electrons, and the number means how many it lost from its neutral state. And that's what a cation is something that loses electrons. And because it loses electrons, it now has more protons than electrons, which is why overall it's positive. And same reasoning for the anion. When it gains electrons, it now has more electrons than protons, and it has more negative charges than positive charges, which is why overall it is negative. So if you have something with a charge, the only sort of adjustment you need to make is to the number of electrons. Again, protons are locked in because if you change that, it's a different element, and neutrons again are neutral, have no really no effect on the charge. Any questions on that there? So you do need to be able to obviously figure out protons, electrons, and neutrons for neutral things, things with charges, mass numbers, atomic numbers, all that good stuff there. All right, so energy, although we don't talk a lot about energy in here, they've taken it out of this class and moved it to 200B for some weird reason. We will come across energy along the way in some of these chapters because, the book kind of assumes maybe you did that chapter, but, we'll talk about those things. So the ability to do work or produce heat, again, the law of conservation of energy, as we might have talked about earlier, we don't lose nor create energy. It can be transferred from one place to the next. When we talk about heat and energy, again, heat flows from hot to cold. There's different types of energy associated. Thermal energy is related to how many molecules and atoms you have. The more molecules and atoms you have, the more vibrations you have, the greater the thermal energy. Chemical energy, for example, there's energy stored, for example, in bonds. When you make and break bonds, energy is transferred out or in to do so. Nuclear energy, potential energy, the position of something, obviously kinetic energy, the energy of motion as well. Some important sort of units that we come across, as we will see in some other chapters, joules is a important unit of energy that we use. Also kilojoules is another unit of energy. We don't really do too much with calories here in this class, really, but it is also a unit of energy. And kilocalories is also another unit of energy is sometimes used. The relationship between joules and calorie, 1 calorie is 4.184 joules. That is also the number, if you remember, maybe specific heat. The specific heat of liquid water is 4.184 joules per gram per degree Celsius. A relationship that we actually will kind of see along the way in a couple of spots is actually this one. 1 joule is equal to a kilogram meter squared second squared. So that sort of relationship sometimes pops its head up. I think it will in the next chapter. So just keep that in mind. And really, in our sort of context, what it means for you is you do have to kind of do a conversion of grams to sort of kilograms, so everything works out correctly to get it to joules. So that relationship we will see. All right. And again, here's, as I mentioned before, some of our energy units along the way. All right, that wraps up chapter 1, I think. So we're going to roll to chapter 2. If I find the chapter 2, and in this chapter, we're going to talk about atomic structure, as it says, and the periodic table and some other things, electron configuration, quantum numbers, some other stuff along the way here. So the first thing we're going to actually talk about is the idea, and really the main sort of idea of this chapter is something we talked about the other day. And we're going to really kind of focus in on electrons and the idea of electrons, again, sort of transitioning, for example, from a lower energy level to a higher energy level. And as we talked about the other day when we did flame tests, that's sort of what you did to it when you put, your sample into the flame. As we also talked about, essentially what will happen is these electrons do want to sort of relax back down to a lower state of energy because of our conservation of energy, the atom itself in that situation would have to give off that energy in the form of a photon of light, which has a specific wavelength. And as we talked about last time, if that wavelength, for example, is in the visible part of the spectrum, you'll see some type of color associated with that. Hence the fireworks. That's essentially what's going on there. They explode the fireworks with a lot of energy, excites all the electrons of the elements that are there. And as those electrons relax back down, we go pretty colors as we're eating our hot dogs and all that good stuff on 4th of July, or you're at Disneyland or whatever it may be. But that's essentially what's sort of happening there with our sort of fireworks. So why do we get colors? Why do we get different chemicals gives us different colors? There's a couple of reasons. Again, we get different colors depending on what electrons are transitioning and really what electrons are transitioning from what energy level to the next. The idea as they transition from one energy level to the next will result in perhaps a different wavelength of light coming off, and that different wavelength will have a different energy associated with it and would represent a different color. And again, depending on how many electrons something has as to what distinct colors you may see. One of the things we will talk about in this chapter is that every element, for example, has a specific sort of colors or lines that happen as these electrons transition, and different wavelengths that occur as well. Now, electromagnetic radiation is one way in which energy is sort of transformed through space, and it's transformed on a wave. So when we talk about a wave, it has a few characteristics, such as this. So this is a wave. One of the characteristics of a wave is what is known as lambda, and that is its wavelength, and that is the distance between two peaks or two troughs, which are on the bottom. The frequency of a wave is really how often a wave passes a particular point in a second, and the speed of a wave, obviously, is how fast that wave is moving. Put in our symbols there. There we go. So as I mentioned before, lambda is the wavelength. I would say, typically speaking, meters, nanometers, and sometimes centimeters are common wavelength type units. A lot of times, if you are using a wavelength in a calculation, meters should be the winner there, so everything cancels out correctly. Frequency is the number of waves that pass a particular point in a given second. That is nu, it's really not a V, so that is nu, is the symbol there. In terms of frequency, typical units of frequency are reciprocal seconds, which is basically 1 over a second. And a reciprocal second is also equal to 1 hertz. And a hertz is also a unit of frequency. They're a one-to-one relationship. For example, megahertz is like when you dial your radio to a specific radio station, like 95.5 megahertz. That is the frequency for that radio station that is sending out radio waves that you can hear, right? And music comes through your car. The relationship between those two things is c, which is the speed of light, 2.9979 times 10 to the 8 meters per second. I'm good with 3 times 10 to the 8 meters per second if you want to roll with that. But if you want to use the other one, people seem nowadays to be fond of rolling with the whole number there for some reason. But I'm good if you want to go 3 times 10 to the 8. I probably will use that one in most cases. So we have c is equal to the wavelength times the frequency. The speed of the light is meters per second. So that is meters per second. The wavelength, when you use this formula, does need to be in meters. The frequency should be in reciprocal seconds, and that is how we get to meters over seconds in terms of our speed of light. That means if you know the frequency, you can figure out the wavelength of light that's associated with it. If you know the wavelength of light, you can figure out the frequency associated with it. The good news is it's really the same calculation regardless of which one you have. It is the speed of light divided by the other thing, so the frequency there, or if you want the frequency, it's the speed of light divided by the wavelength. Again, a reminder that the wavelength should be in meters for everything to work out correctly. All right, so why don't you try one here? Calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14. Let's do it in nanometers. Why not? Good reminder. Nano is 10 to the minus 9. So see what you come up with on that. Are looking for the wavelength. We are given the frequency here, which is 4.62 times 10 to the 14 reciprocal seconds. Again, we always have the speed of light, 3 times 10 to the 8 meters per second, or you can use obviously the 2.9979 number if you like. In this case, we're going to solve for the wavelength. That's going to be C divided by our frequency, and that's because C is equal to the wavelength times the frequency in this case. So we're just dividing that to the other side. Putting in our numbers here, we're going to go 3 times 10 to the 8 meters per second divided by 4.62 times 10 to the 14 reciprocal seconds. The seconds will actually cancel each other out, and that will get us here. You definitely want to make sure you're using your exponent button when you punch that in. That is going to get us basically 4.49 times 10, not 6. It's like a 4, but a few more numbers. 6.49 times 10 to the minus 7 meters in this particular case. That would be obviously the wavelength there in meters, but we were looking for it in nanometers. So just a reminder, which would also be good for today's lab. Nano is 10 to the minus 9, so what that means is in 1 nanometer, there is 10 to the minus 9 meters, and that is the correct way to use that. It does not mean that there's 10 to the minus 9 nanometers in a meter, right? So people always reverse those things. By the way, 10 to the minus 9 is 1 times 10 to the minus 9 if you need to put that into your calculator. We'll do a little dimensional analysis here. Meters on the bottom, 10 to the minus 9 meters on the bottom, a nanometer up on top. Meters will cancel, so we're basically dividing this number by 1 times 10 to the minus 9, and that's going to get us 649 nanometers as our wavelength. Any questions on that one there? All right, let's see here. Hopefully they agree. Looks like they do, so that's good. All right, so let's try this one here. We got to calculate the wavelength of a radio signal. That is 100.7 megahertz. I'll spit that out. We could do this one in meters just fine. Mega is 10 to the 6th. Maybe I'll write right. There you go. Mega 10 to the 6th. Okay, so let's take a look. In this case, we are looking for the wavelength. In this case, we do have the frequency given to us, which is 100.7 megahertz. And again, we always have the speed of light, 3 times 10 to the 8 meters per second. C is equal to the wavelength times the frequency. I personally am going to take this megahertz into a hertz, which is basically equal to a reciprocal second. So I got everybody kind of in the right units. Otherwise, if you kind of roll with it the way it is, you're off by a factor of 6, 10 to the 6. Yeah. That's a reciprocal second, and that's the typical units of a frequency, and it is equal to a hertz. It's a one-to-one relationship, kind of like a milliliter and a cubic centimeter equal to each other in a sense. It's kind of the same sort of deal. So in this case, what we're going to do is take the 100.7 megahertz. Once again, what that means, 10 to the 6 for mega. That is how much in one of the prefix units there is in the base unit. So there would be in 1 megahertz, 10 to the 6 hertz. And we'll use that as our conversion here. Megahertz need to go in the opposite location on the bottom there. 10 to the 6 hertz up on top. Once again, set up like dimensional analysis, multiplying on top, dividing on the bottom in this case. And that again is also the same idea. That is 1 times 10 to the 6, basically. So 100.7 times 10 to the 6 there, going to get us a 1.007 times 10 to the 8 hertz, which is also a reciprocal second. So again, it's a 1-to-1 conversion between those two. So now I have everybody kind of in the right units. I'm going to solve for the wavelength, which is c divided by the frequency. We'll go 3.0 times 10 to the 8 meters per second. I'm going to use that number I just calculated there in the units of reciprocal seconds. That way our seconds cancel out. And that's going to leave us with meters, which is good because that's what we're looking for. And in this particular case, we will end up with about 2.98 meters, which is a typical wavelength of radio waves in that sort of distance. Any questions on up there? Also a much longer wavelength than, say, our red light there, which is a visible part of the spectrum, which is much smaller wavelength. Any questions on the calculation? Yeah. You could use that. What's that? You could use it. If you want to use it, you can. If you want to use 3 times 10 to the 8, I'm good with that. You can use either one. It's perfectly fine. Yeah. Nowadays, they seem to have rolled back to, I want to use more digits. So a lot 2.9979. But if you want to use that number, it's perfectly fine. You, in all reality, will probably get pretty close to the same answer, I think. Other questions? Or if you want to use 3 times 10 to the 8, I'm good with that as well. All right. So let's talk a little bit about waves. Waves, again, are how energy is sort of carried through space. There is a relationship between the wavelength and the energy and the frequency. If you have something with a long wavelength, such as this. So if you have a long wavelength, you usually have a longer frequency, and that usually is a lower energy than if you have something with a much smaller wavelength, such as this. So if you have a smaller wavelength, that usually results in a sort of higher frequency. I guess lower frequency would be a better way of wording that. And that also is higher in energy. So these are 3 wavelengths. One's red, one's green, and one is blue. And we can see here, this guy has a longer wavelength. It would be lower in energy than, say, our blue down here, which has a shorter wavelength. It will be higher in energy. So again, even within colors, as we might have talked about when we did the flame test, there is a difference in terms of energy. Red, for example, like we calculated in that previous example, has a much longer wavelength than, say, purple or violet sort of color that's coming off. And red is lower in energy than, say, purple side of the Roy G. Biv sort of colors. So speaking of that, this is the electromagnetic radiation. And when waves come off, they have a specific wavelength associated with it. And they may fall somewhere on the spectrum. So on this side, we have a wavelength at 10 to the 4th. That's a longer wavelength, which means on this side, it would be a lower energy. Over here, this is 10 to the minus 12, which is a shorter wavelength, which means it will be higher in energy. So down at this end, we have radio waves, like we just calculated. And again, that has enough energy. We can hear, obviously, sound through them. That's what comes through our radio. As we go to the left here, a little shorter of a wavelength, we have microwaves, which has a little bit more energy associated with it, enough to spin water molecules really fast. You could have like a pizza in 3 minutes, right? And all that good stuff. Infrared, even smaller wavelength. Again, this is where Typically heat is sort of felt from. Then we have the visible part of the spectrum. That again is where we see color. We have our Roy, right? G Biv, I guess. Going this way. And even within, again, the visible part of the spectrum, we can see red over here, kind of 700 nanometers, having our lower energy, longer wavelength. And again, as we talked about, more of our violet at this side, shorter wavelength, higher energy. Then after that, we have ultraviolet, UV, right? That's why we throw sunblock on so we don't get too burnt out there. Yeah.
So I get the concept of like radio waves, all that. But how does, for example, in the problem did where each wave, how does that correlate to the sound we hear? Is it that like smaller vibration?
Yeah, it has a certain frequency associated with it that we're able to hear, right? As opposed to maybe different wavelengths, which has a different frequency that we can't pick up, right? And like, for example, animals can hear things we can't hear, right? Because they can pick up certain frequencies that come through at different wavelengths and stuff like that. So that's sort of the idea with that. Ultraviolet, which again is UV, a little bit stronger energy, as I mentioned before. Why we get sunburns and stuff like that. Why we put sunblock on to try to repel some of those rays at us. X-rays even shorter in terms of wavelength, a little higher in energy. Why they throw a lead vest on you when you take an X-ray, right? And why they leave the room typically when they shoot the X-ray. And gamma rays, as we talked about in the last chapter, is really just pure radiation. They're not. They have really no charged or neutral rays, but they're very, very high in energy. You ever use gamma rays or a gamma emitter, a radioactive sort of substance that gives off gamma rays, you need a lot of specialized sort of protection to protect yourself so you're not absorbing all that energy that comes off of it. So this is electromagnetic spectrum. What we're really relating this to in this chapter again is as the electrons transition, they're going to give off energy in the form of a wave that will correspond here. So although we kind of focus a lot on colors and the visible part of the spectrum, transition of electrons does not necessarily mean that they will always transition and give off something in sort of the visible part of the spectrum. They could give something off in the infrared part of the spectrum. They give something off in the ultraviolet part of the spectrum, where we obviously would not see colors again because we're not able to obviously see that. So sometimes people think, oh, whatever electron transition, it's always going to come, from this part of the spectrum, but it can actually come from any part of the spectrum along the way. You do need an electromagnetic spectrum. I don't anticipate asking you specific, like where, the exact wavelength where any of these sort of break out, but you do need to know it in order of like longest wavelength to shortest, highest frequency to lowest, highest energy to lowest. That also includes the visible part of the spectrum with the colors. You need to be able to kind of put those in that same type of order. Any questions on that there? Okay. That's a pickle. A random picture might come in. I don't know. So as we're talking about energy and as things transition, one of the main ideas of sort of quantum mechanics, which is sort of what we're talking about in this chapter, is that energy can be gained and lost in integers of multiples of energy. And these are sometimes referred to as a quanta of energy, this sort of packet of energy. And energy seems to have a particle-like property in addition to sort of a wave-like property. So there's sort of this dual nature of light where, they can have characteristics very similar to what waves do and also characteristics similar to these sort of packets or streams of particles. The idea of quantized energy and sort of what we're talking about, you can kind of think of it as a simple sort of idea of as an electron transitions in a quantized sort of fashion, it will gain or lose enough energy to fully make that transition. So it will either gain enough energy, get all the way there to the top, or if it's losing energy, it will lose enough energy, say, to get to this energy level. It will never sort of stop in between. So you can think of the quantized sort of idea of energy and sometimes oftentimes sort of referred to as like a staircase, right? So if you're walking stairs, you're either on this step, right, this step, or that step, or whichever step you're on. You usually have enough energy to get to those steps. You never, like in between steps, decide I'll just take a rest right there and see what happens because you're going to fall, right? And it's sort of the same idea with quantized energy. Electrons will gain energy and also lose energy in that fashion. They will either gain or lose enough energy to fully make those transitions from maybe one energy level at a time, maybe 2 energy levels, 3 energy levels, whatever it may be. Kind of similar to steps. Some people could walk 1 step at a time. Maybe some people could do 2, maybe 3. I don't know. But some people could do multiple steps at a time, right? So electrons can transition. You don't always have to go like just one shot down or not. You could also make a relatively good estimate, for example, as to when you do see a color as to maybe how far that transition may be. If you see a red sort of color coming off, that is lower in energy, which means maybe that electron only dropped 1, right? As opposed to maybe you see a color like purple coming off, maybe that electron traveled many energy levels and that had to be given off a lot of energy along the way. So, based on some colors that you sometimes see, you can maybe make an estimate as to how far that electron is transferring. So energy is quantized. Electromagnetic radiation is a stream of particles called a photon of light, and that again is usually given off. There's sort of 2 ideas here, right? One sort of an endothermic, exothermic idea. A lot of times we focus on emission spectrums, which is the idea when electrons sort of transition downward in energy and the atom gives off that energy, sort of emits that energy. And also the opposite of that is an absorption spectrum. For example, when you actually put energy in, kind of like when you hit it with the Bunsen burner and you add the energy and you measure what the electrons going upwards in energy as opposed to coming downwards in energy. Now, we can calculate the energy of a photon, and that's what was missing there on that last slide. I knew it was something. By E is equal to H times the frequency. This is the energy that results from a photon of light. H is Planck's constant, and it is a constant, and it is 6.63 times 10 to the minus 34 joules times seconds. So that is a value you always have. 6.63 times 10 to the minus 34 joule seconds is Planck's constant. So what that allows you to do is you could figure out the energy associated with a wavelength with a photon of light if you do know the frequency. We could also tie together this equation and the one we saw earlier and solve for the frequency, which is c divided by the wavelength. And if we take that and put that into here, we get this version of the equation, which is the energy is equal to, I'll put it in here, I'm not sure where they all went. E is equal to hv, which is equal to hc over the wavelength. So this allows you, if you know the wavelength, you could also figure out the energy associated with it, as h is Planck's constant and c is still our speed of light. So it does give you a few different ways that you could calculate that energy associated with it. Again, if you know the frequency or the wavelength of that photon of light, you can put it into this equation and get it. Unit-wise, what you're going to end up with here is joules. H is joules times seconds, and the frequency is reciprocal seconds. These two will cancel out, and you will end up with joules. Same thing over here. H is joules times seconds. C is meters per second. And the wavelength here is in meters. Meters cancel, seconds cancel. You're left with joules. So you should end up with joules when you use this formula and calculate the energy associated with it. Any questions on that there? All right. Now, as I mentioned before, there's always this idea in Einstein's equation there equals mc squared of this dual nature of light. Electromagnetic radiation is this idea that, again, particles can have wave-like functions and waves can kind of behave as particles as well. So what happens when these electrons get excited, we do get kind of 2 types of spectrums that sometimes occurs. One type of a spectrum is what is known as a continuous spectrum. and that is when white light is passed through a prism. It basically contains all the wavelengths of visible light as opposed to a line spectrum. And things like the sun, for example, give off a continuous spectrum. Everything sort of just comes out at once, basically. A line spectrum is distinct lines at specific wavelengths that correspond to different electrons transitioning energy levels. So a line spectrum, much like it sounds like, is individual lines like you will see today in lab. And this is an idea of quantized energy. Quantized energy, again, is we're going to get these electrons specifically transferring from, say, like the third energy level to the second, going to give off a specific amount of wavelength of light with a specific wavelength and give us a specific line. So we talked about quantized energy as sort of like stairs. The way you could kind of think of continuous spectrum is like a ramp, right? So instead of walking the stairs, if you walked up a ramp, you pretty much can lay it up anywhere you like, right? On that ramp, you're going to be okay. And that's like everything could come out as once, rather than if you're quantized, you got to be here, 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 and here only. You can't be really in any other locations. So, and that's again a result of those electrons gaining or losing a certain amount of energy. So very much like what you're going to do today, you're going to have a source, and one way you can do that is an electron discharge tube. You throw electricity through it, excites the lamp that has the elements in it. Those electrons are going to basically be excited. And again, if it was more of a continuous one, you would see basically a rainbow of everybody coming on at once. What you should see in a metal, such as or an element like we have, you'll have these distinct lines again representing the different electrons transitioning from different energy levels. Every line spectrum is different. Every element has its own unique line spectrum, which means, if, for example, hydrogen and krypton, or zinc, or whatever it may be, look at nitrogen, neon, they all have different lines at different wavelengths and different sort of colors in some cases, and you can distinguish what the element is based on the lines you see and what elements they're present. So here's that idea.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So here is the hydrogen emission line spectrum, and again you can see 4 distinct sort of colors come off at different wavelengths and have different colors. And again, like I mentioned before, each of these are a result of electrons transitioning. As we talked about earlier, that is red, which might be a result of a small transition, right? Because red is lower in energy, which means a small transition would get off a lower amount of energy, rather than this transition over here is probably several energy levels, which would require the atom to give off a lot more energy as it's dropping from one energy level to the next. The electron, the atoms can give off all that energy. So when we talk about this, only certain energies are allowed for an electron in a hydrogen atom. Energy of electron in a hydrogen atom, again, is quantized. We see that because we get those line spectrums rather than everything happening all at once. All right, here. So why is it significant that the color emitted in hydrogen is not white? Again, that means we're getting distinct lines coming off, right? If it was white, that means it's more of a continuous spectrum. Everything's coming off at once, as opposed to what we see there. Individual lines representing really, again, our electrons fully dropping from one energy level to the next. The result of that, again, that energy being given off as a photon of light. That brings us to sort of the Bohr model of the atom. And the idea of the Bohr model of the atom is this sort of planetary model. And the idea was you have sort of the nucleus and you have these orbits, right? And within these orbits, you have these electrons going around and kind of orbiting in nice, pretty circles. And Bohr's model, as we'll talk about, worked really well for hydrogen, but does sort of fall apart as you move away from hydrogen. Something that has a lot more electrons. It doesn't work very well, but it does nicely sort of explain the sort of lines that we do see in the hydrogen's emission spectrum, or line spectrum. The ground state is n is equal to 1. That is the lowest state in energy. Anything above that, n equals 2, 3, 4, 5, 6, and 7. Those are higher energy states. They're sometimes referred to as excited states. They are further away from the nucleus, higher in energy as you go from 2 to 3 to 4, and so forth. So the idea here is an electron can be only in this orbit. If not, it has to transition to the next orbit and be in that orbit. Once again, they're going to sort of move from one orbit to the next by gaining quantized energy, enough energy to fully make those transitions. We won't find an electron just hanging out between the rings or anything like that, or the orbits. They will fully transition from one sort of orbit to the next. And again here, as you can see, we have perhaps our red transition here, just one energy level, as opposed to our blue that went from the 5th energy level all the way down to the 2nd energy level. So as I mentioned before, we have our green that went from the 4th energy level to the 2nd, accounting for those 3 of the 4 lines that we see in hydrogen. So this is the idea of the Bohr model, n equals 1, n equals 2. And again, as I mentioned, fully transitioning down, that is our E is equal to H times the frequency. That is the energy associated with those transitions as we go through there. Now, one of the ways that you can calculate the energy required to transition from one energy level to the next is one of the ways we'll do in lab today, which is this equation here. The change in energy is equal to minus 2.178 times 10 to the minus 18. This is what is known as Rydberg's constant. That's Rydberg's constant. 1 over n squared final, that is the final energy level the electron finds itself at. And again, n could have values of 1 through 7. The final energy level. And n squared initial is the initial energy level. Now, this delta E is equal to the same thing we saw before, h times the frequency, also equal to hc over the wavelength. So they're all equal to each other. When we calculate the change in energy, it is important to keep the negative sign if you do get a negative sign, because a negative value of E is a exothermic process. And that would mean that the atom is releasing that amount of energy. If you end up with a positive value for E, that is an endothermic process. And that means the atom's actually absorbing energy. That happens in one of two ways, right? If I have an electron on the first energy level and it gains energy, the atom, it's going to excite that electron to a higher energy level. And for the atom, that is going to be an endothermic process, and it would absorb energy in a positive number sort of fashion. When I have that electron starting up there on the 3rd energy level and decides to drop to the 1st energy level, the result of that happening is the atom's got to give off that energy in the form of a photon. And for the atom, that's going to be an exothermic process. So when you calculate delta E in this case, you should end up with a negative number. So if your transition is your electron starts at a lower energy level to a higher, when you calculate delta E, it will be a positive endothermic sort of process for the atom. If your electron starts on a higher energy level and ends at a lower energy level, that atom's going to give off that energy and you're going to get a negative. So it's really important when you use this formula, which you'll use later on today, when you do calculate energy in general, you get a negative number, you should keep it because it tells somebody this is sort of an exothermic process or an endothermic process. Now, with that being said, when you go to use that energy value then to calculate something like the wavelength or the frequency, you should just get rid of the negative sign, because you should not end up with a negative wavelength or a negative frequency. So when you give sort of the answer with this type of problem in lab and also in these type of problems for energy, you keep the negative or the positive. But when you go to calculate something like frequency or wavelength, you got to get rid of the negative sign on the energy value. And again, that will get you a positive value for wavelength or frequency. If you don't get rid of the negative sign, you'll get the same number, but it'll be negative, and you can't really have that negative sort of wavelength or frequency. So sometimes that confuses people. You got to just dump the negative sign after the energy calculation and use the positive version of it to calculate frequency and wavelength, so that those guys end up as a positive number. Any questions on that there? All right, so we did get to this one, which is good, I guess. So that will help us for the lab. So we'll lay it up there.